Good morning or good afternoon, everyone, depending on where you're joining us from. My name is Georgia Marchant and I am PR and social media lead at Fluke Reliability, which is home to eMaint and Proof Technic. We've got a truly special webinar today. Our speaker is John Bernet, product specialist at Fluke Reliability, and he's going to talk to us about industrial Internet of Things and vibration-based condition monitoring. And is it a false dawn? We've still got a couple of people logging in, so we'll just give them a minute or two to get settled, and then we'll get underway. You can still see a couple of people joining. Cool. Okay, I think we're ready to go. We'll just let anyone else sort of join in as and when they can. Thank you so much for joining us for today's webinar, which is titled IIoT and Vibration-Based Condition Monitoring, a False Dawn. As I mentioned, our speaker today is John Bernet. Before I formally introduce him, I'll cover just a couple of housekeeping topics. Today's webinar is being recorded and we will share a link with you after the event. So you'll be able to find it on the Fluke Reliability YouTube channel as well if you'd like to revisit the content or perhaps share it with someone in your organisation. As always, we do also invite your comments and questions. So there's a Q&A chat box on your screen. If you think of a question for the speakers at all during the talk, either pose it to our speakers at that time or just hold it for the discussion portion at the end of the event. As I mentioned, today's presenter is John. John is a mechanical application and product specialist within Fluke Reliability. He works with customers from all industries to successfully implement their reliability programs. John has more than 30 years of experience in the maintenance and operation of commercial machinery and as a nuclear power plant electrician in the US Navy. He also holds a Category 2 Vibration Analyst certification and is a certified maintenance reliability professional. Thank you so much for taking the time to present for us today, John. With that, I will hand over to you for today's talk.
Thanks, Georgia. So let's get started. So what we're going to be talking about today is a lot of the things that we've been seeing over the years and hearing a lot of buzz about the Internet of Things is coming to fruition with condition monitoring, and we're seeing a lot of so here's kind of an overview of what we're going to be talking about today. I'm not going to get real deep into this because you're going to see each of these and you may have already seen this overview, but we're gonna talk a little bit about each one of these as we go through and talk about how the Internet of Things is going to be affecting condition monitoring. So let's just jump into it. So what we're seeing is, and keep in mind that this condition-based maintenance and vibration analysis and reliability and improved maintenance has been around for many years. It's not like we're reinventing the wheel or we're redesigning it. It's just a way of using today's communication and other advancements to make things run smoother and give us a nice fresh way of doing what we've been struggling to do for many years. And so many of you have probably already seen this P to F curve, the potential failure curve, where we talk about before a machine fails, that there are many different things we can use to look at that. Well, let's talk a little bit about, and the idea is if we can improve the way that we do maintenance and reliability, we can push our P to F curve to the left. And so what we're talking about here, we're going to walk through each of these steps real quick, is even before we talk about this potential failure curve and acquisition of condition monitoring data, we want to talk a little bit about installation, because if you already have machines in a bad position, or if we can make machines be a little bit healthier, it can help us out. So let's jump into each one of these steps real fast. And so what I mean by that is by using precision alignment and balancing up front, we can make our machines be a little bit closer to the left side of that and further away from failure, because the name of the game is to try to know, run a machine as long as you can, and also to know when a fault is happening. Now, we're not saying that you have to go out and precision align machines and balance machines at the beginning, but somewhere along the line, we need to get machines in their best possible shape to get the most life out of a machine. So even before acquiring data, we should make sure our machines are in the best possible shape. And then we start acquiring the data. Good data is paramount to getting good information. And so a lot of us have tried and maybe weren't successful with route-based data collectors over the years, and there's a wide variety, and you see some examples down at the bottom of vibration tools and ultrasound tools and thermography tools, and some of these are route-based, and some of these are sensor-based to a cloud, and some of them are very simple and some are very complex. So we're going to talk a little bit about that. That the first step of getting answers is to start with data and connecting that data, not just getting a bunch of numbers from a lot of different tools. So the next step we want to talk about is getting data from multiple tools and multiple technologies, and from people, and from observations, and from pictures, and enriching that data to get answers from it, because numbers on a chart, in a spreadsheet, in a desk, in a file cabinet isn't doing us any good. So connecting that information and getting answers out of that data is really a key point. And then finally, we need to act on it. So we don't just do condition monitoring to get a bunch of numbers. It's kind of a multi-step process, and the end result is we want to be able to find out if the machine is good or bad. We want to find out what the fault is. We want to know how bad the fault is. We want to generate work orders so that we can go out and fix our machines. We can keep our plant up and running. So that's why this Internet of Things is so appealing and so refreshing, is because maybe now we can finally connect our data, connect our teams, connect all of this together and get answers and get real solutions. So that's what we'll be talking about. And it's connected knowledge services. What we find out is, we need to make sure we bring in our experts. And, with remote, since COVID, we're seeing more and more things are remote this and remote that. Well, let's share information with experts, and let's have our experts help us out. And maybe, getting that information remotely through cloud-based programs is the way to do that. So now that we've kind of introduced this idea and this concept, let me jump a little bit into vibration analysis. Some of you may be quite familiar with vibration analysis. Some of you may not have a clue about vibration analysis, but let me run through some real quick ideas about condition monitoring with vibration analysis. And that is, the purpose of this is so that from the vibration of the machine, we can know the condition of the machine and fix a machine in advance and have fewer parts. A lot of people, when they first hear about this concept of using vibration, they think that it's easy. Basically like a temperature or pressure, it's just a number. Well, and they think that if all they knew was the vibration, they would somehow automatically know what is good and what is bad, and when the vibration got high, they would fix the machine. Well, let me tell you, it's a little bit more complicated than that. So the bad news is vibration is from a machine is very dynamic. It's like an EKG on a person. So if you think about it, there's not just an increase in vibration could be from not just a fault, but it could be from background noise, adjacent machines, the structure, resonances, changing load and speed. And so somebody could have started up an adjacent machine and the vibration could increase. And what is the vibration level that you need? So it isn't just like it isn't just a number, and we can't just magically watch that number. The good news is vibration experts been analyzing, data for 30, 40, 50 years and have a good idea that, what does a mechanical fault has a pattern. And so the algorithms and rule bases that vibration experts have been using, can tell us, is it noise or is it structure or is it a fault? And so, but what I'm trying to say is, it isn't just a simple number. It's like a doctor having to read an EKG. So the other thing is, a lot of people think that if they would, they needed to do this when the machine is new. Well, I can tell you from personal experience that just because a machine is new doesn't mean that it's healthy. And so what we really want to do is look at the machine and watch it over time and look at patterns and look at different machine types, because we know that vibration from a certain type of machine, motor coupled pump, is going to have certain vibration and certain patterns, and so we can learn from that. And so what I'm trying to say is, there is no black box, there is no magic secret formula, but from lessons learned that we've been looking at machines in the over the years, is that we know what the patterns look like and we can follow some best practices. And also, don't do this on your own. It isn't something, you're going to need some help to, and we'll talk a little bit more about that. So the next thing, and again, I apologize for vibration experts that are on the call that already know this, but for those that aren't vibration experts, let me kind of do a little bit of an explanation on what vibration is, because a lot of people have this idea, again, that vibration is a simple number. And there's really 3 different types of vibration. And as you see here, way over on the left is the raw vibration data, which is very complex. Really it takes a vibration expert to read it. And then way over on the right is the simple vibration. So a lot of the vibration sensors and tools you'll see in the market have simplified it. Well, maybe they've oversimplified it. So let me talk a little bit about what I mean here. So way over on the left is the complex, the raw waveform that we collect. And that raw waveform, has all of the information, but it's jumbled up, and it takes advanced analysis to be able to get all of that out. And I've been doing vibration analysis for 35 years now, and I can tell you that it takes a lot of time and experience to learn how to look at that over on the left to get the answers. I'm not saying that that's good or bad. I'm just saying that just one type of vibration analysis. Way over on the right is the simplified vibration, where you take all of that vibration and over a wide frequency band, and you take all that energy and you average it and you get just one number. Well, that's really good because it's a nice simple number, but unfortunately there's not a lot of information there. It doesn't tell you, is it noise? Is it background? Is it resonance? Is it a fault? What fault is it? How bad it is? All it tells you is like a check engine light in your car. And so a lot of people have this idea that if they knew what the vibration number is, they'd know what to do. Well, unfortunately, unless you know your machine and you're a vibration expert, that's not the truth. So way over on the left is very complicated, that you need an expert. Way over on the right is very simple, but you don't get the information you need. So in the middle is kind of, what I call maybe the happy medium, or the Goldilocks, where if we look at the frequency data, the spectrum, there are what the frequency, and I'm not going to make vibration experts out of anybody in this short meeting, but what I do want to tell you is that by looking at the vibration spectrum, we can simplify the time waveform on the left, but not simplify it so much that it loses any information or any answers. And so you see that one in the middle, that by looking at repetitive patterns inside the time waveform, we can identify imbalance, misalignment, looseness, and roller bearings. And if we can quickly and easily identify the faults, then our maintenance teams know what needs to be fixed. And so what I'm saying is we need to use the right vibration analysis technique for what you're wanting to do. You know, if you have very complex machines, you're probably going to need the time waveform. If all you want to know is the machine healthy or not, then a simple trend over on the right is all you need. But in most cases, in most plants, the maintenance teams need to keep their plants up and running, and they need to know, they don't want to, see complex data, and they don't want to know, what a number is. They want to know what is the fault, how bad is the fault, what do I got to do to fix it. So keep that in mind as we're talking about vibration analysis. So we need to get answers, and I've already talked about that. All right. So with a lot of the new things coming on the market, we're seeing a lot of low cost and low power sensing technologies, and they're all promising to be able to give you success. But what we've been finding out is that when you look at a customer's goals of wanting to be more proactive and cost savings and continuous improvement, to actually deliver that and have a successful program over on the right, where you really see more uptime, better cost, more production, better reporting, to get from point A to point B, we can't do that with just simple, easy to use hardware, because like what I showed you earlier, if we just have overall vibration meters, really all that's going to tell us is the machine good or bad? And because it's only collecting in the low frequencies, it's not going to give us any bearing information. So it really isn't going to get us to the point where we get the answers we need, and we need answers to be able to fix the machine. Just knowing if the machine is good or bad doesn't get me from point A to point B. All it tells me is that further testing is needed, and just trending a vibration number does not get me the end result of getting the machine up and running. So what we've learned is that hardware only is only part of the solution. So we need to be able to do more than just a vibration data collection program. So how do we do that? What we've learned over the years is that to bridge the gap between your goals and successful program, you need three things. One is you need a sensor that's going to be able to look in just not just the low frequency, but the low frequency and high frequency. So by looking in the high frequency, we can also see bearings. And like I showed you earlier, we're going to need to be able to look at the spectral data, not just overalls, because we need to look at high frequency to find bearings. We need to look at the spectrum to be able to find the patterns. And the purpose of getting this better data or best solution data is to be able to get answers. Because if all I'm looking for is just a vibration number, then just go for the cheap vibration sensor, but that's not going to get you what you need. Now, when you think about it, some of the obstacles we're going to run into is, how do I build a program when I'm already 100% busy? And how do I make the best decisions if I don't have complete data? So that's really the challenges that we need to overcome. We need to get the best data. We need to get the right data. We need to be able to make it into answers, and we need to be able to get alarm notifications. So to do that, to get the answers from the data, it's going to take software plus the hardware. So when you think about it, if we use broadband alarms, that's going to be able to tell us when something is good or bad. But like we showed you earlier, that doesn't tell me what the fault is and what to fix. So in addition, we're going to need narrowband alarms. So I'm not going to get too deep into this, but basically one is like your check engine light, that's broadband alarms. The other one, narrowband alarm, is like an EKG. It's going to tell you what the fault is and how bad the fault is. With this information, now we can make the right decisions to know when to take a machine down. The challenges that we're going to run into next to be able to get to our goal of a successful program is how to set the alarm levels, and if we have limited resources, who's going to be looking at all these graphs and all of this data? So we're going to need to be able to reach out and get some support. And one way to do that is expert assistance from remote vibration experts. Another is to have programs and support services to give us support and help us grow a program. Artificial intelligence, ways to look at these algorithms. And so it's not just, we have to have somebody look at hundreds of sets of data, but, it's going to mean that we're going to have to think about this, and to get from point A to point B, we're going to need to collect the data that we need to get the answers that we need to be able to then generate work orders and have somebody go out and do it. It's a lot more than just a vibration meter. So having these three parts of the program gives us a solution. A solution is what we need to keep a plant up and running. So when we look at it, there's some key things we need to look at. Is that, does your data give you answers? Do the answers allow you to perform an action to correct the machine? If we fix the machine, are we going to be able to see savings and success? Because that's what gives us a successful program. So let's kind of switch gears a little bit and talk a little bit about the different machines in a plant. And there isn't a one size fits all, in that one vibration sensor or one type of doing it doesn't work in all the machines in the plant. So that's why we need to use connected reliability. We need to connect our teams. We need to sometimes, like in the medical industry, the nurses have one task, the general practice doctors have another task, and the specialists have another. So if you look at the production critical machines in a plant, they need a lot more. Well, that's like your specialist, your specialist doctor, because in addition to the most common faults, you also need to know resonances and structures, and these high-end machines need a lot of high-resolution data, and they need vibration experts and machine experts to be able to analyze it. And that means they're going to need wired vibration sensors and sophisticated software programs. So what I'm saying is that's one group of machines. The other machines in a plant, if you look over at our pyramid over on the left, at the top of the plant are your most critical and most complex. Below that are very critical and less complex, and the mainstream but less critical. And as you move down these tiers, you can see there's really two groups of machines. At the very top are the machines that we really need to have machine experts that are probably already watching these very, very critical machines. But in tier 2 and tier 3, there are hundreds or maybe even dozens or hundreds of machines that are still very critical, that are breaking down, that we need to keep up and running. And these machines aren't as complex and don't need as much data as the others. And so as you can see, we can start to think about not having to have so much data as needed to get our answers. So short burst of high resolution data is probably going to be enough to be able to find the most common faults. We don't have to have all this high resolution data as you do with the turbine generator or the paper machine. If you're looking at motors, pumps, fans, compressors, and blowers in your plant, those machines, we could use wireless sensors and portable walk-around tools. And then down here at the bottom, we talk a little bit about machine learning and artificial intelligence. So the nice thing about, we need experts for the top tier machines. There is no way around that. We can't automate that. We can't use artificial intelligence. We can't use machine learning. There's just very complex data, and we need experts to be able to watch those. But the rest of the machines in the plant, the 90% of the machines in the plant, we can look at patterns, we can look at common things, we can use best practices, and we can start to use things like, machine learning and algorithms and artificial intelligence to start finding a more effective way of running the plant. Okay, so in the past, I've been showing you kind of from left to right. Let's look at this as more of a life cycle of a machine. So kind of another way of looking at this, or maybe think of this as the same way, but just in a life cycle of a machine. If we start with the green, a machine has just been overhauled. The machine is healthy. We have no alarms, and for many, many months, as we're taking broadband alarms, your check engine light, and your narrowband alarms like an EKG, we're seeing that the machine is healthy, and our alarm notifications are saying everything's good, everything's good, everything's good. So we don't have to do anything. So that's a nice thing about using a connected reliability condition-based maintenance program, is that once we get our program set up and we're monitoring our machines, no alarms for months and months means we don't have to do anything. Once we start getting some broadband alarms, like a check engine light, then we might have a work order that says, hey, we're starting to get these problems and we need to go look at the narrowband alarms, because remember, the narrowband alarms in the yellow, that's where we start to see some patterns occur. But if we don't see any patterns of faults, then we can say, oh, well, that's just noise or an adjacent machine. The broadband alarm is just saying we have high vibration, but there's nothing wrong with the machine, and we just close out the work order. Months later, and keep in mind, this process, we're talking 12 to 18 months. When I was monitoring machines in the Navy years and years ago, we would track, motors, pumps, fans, compressors, and blowers, and using vibration analysis, we could watch a machine go from good to slight to moderate to serious to extreme over a 12 to 18 month period. So this isn't something that happens overnight. So now here it is, months and months later, we're starting to see our narrowband alarms, and the narrowband alarms are starting to say, hey, we might have imbalanced misalignment bearings or looseness. We get a work order that's automatically generated that says, take a quick look at your data, and your data says, hey, the fault is still very minor. So we close out the work order and we just keep watching it. Just because you have high vibration doesn't mean you have a fault. Just because you have a fault doesn't mean you have to fix something. Because if I have noise, then I don't need to fix it. And if my fault is very low, then I still have months. And so you just watch the trend of the fault to see if it's time to monitor, it and keep an eye on it, or if it's time to repair it. Finally, over here in the red, the narrowband alarm is getting higher. We look at our data, the fault is now extreme. We go take a look at the machine, it's starting to make noise, and the work order is we say, okay, you're right, it's time to look at it. We approve the work order and we send somebody out to go fix the machine. And then finally, over here in the blue, we overhaul the machine. After we overhaul the machine, we take vibration levels, everything's back to normal, we close out the work order, and everything is done. So by using these types of reliability programs, we can track a machine, and by using narrowband and broadband alarms, we don't get notified when there's nothing going on, or we only know when we have to do something. The last thing I'm going to roll into, and in the last couple of slides here, is don't do it on your own, because there's a lot of people out there that can help. And so we're going to talk a little bit about companies like Fluke Reliability that's there to help you as you go from so think about it. Well, let me not get ahead of myself. So remember, we talked about the goals to try to improve your maintenance and get things going better. And then over on the right is the success. That's what consultants and vibration and reliability experts are there to help you do, is to get from point A to point B and guide you past the obstacles along the way. Because what we want to help you do is get a successful startup of your program, a successful implementation, and then sustain your program for years and years to come. Okay, kind of as a summary, again, just a different way of looking at this. The lessons learned that we've seen over the years is that if you want to get from your goals of an improved maintenance program to the success of a program that's really starting to deliver and give you what you want, that you need to have the best solution hardware, but it's not the only answer. So you need to be able to get the data you need. Remember, high frequency data, and you need to be able to get the spectral data, because we need to be able to look at patterns. Overall vibration in the low frequency only isn't going to give us the information we need to get the answers. And so to be able to complete that, we then need to take the data from portable and online and wired and wireless systems, get that data into a common cloud portal using automated diagnostics, using AI, using advanced analysis, linking this data to vibration experts, and then sending this to a computerized maintenance management system that can automatically generate work orders. And for those that aren't vibration experts and or have limited time and experience, reach out to those vibration experts and reliability experts that can help you start the program, can help you implement the program, help you grow and sustain the program, because it's more than just getting a vibration sensor, slapping it on a machine, and looking at vibration trends. We need to be able to get answers out of it and be able to generate work orders, get the information to the right people to go out and fix our machines. Okay, well, I got through that a lot faster than I thought I would. So we have, which is good, because now we have some time for questions. So let's see what kind of questions we have.
Thank you so much, John. That was great. Really insightful, fascinating presentation. As a reminder to everyone, today's webinar was recorded and will be posted on the Fluke Reliability YouTube channel. And we'll also send out a link to everyone who attended. We do have a few different questions here. If you have a question that you haven't submitted, please feel free to enter it in the Q&A chat box right now. And we're going to go through as many questions as time allows. And just as a reminder, the deck will be available after the presentation. We'll share it as well as a recording of today's sessions. So just to start us out here, John, I have a question here. What is the best way to start a new condition monitoring program?
That's a great question, and I would say that what really causes the biggest problems to starting up a new program, what causes programs to fail? The number one reason is customers often try to start too big. And what I mean by that is, if you've got hundreds or even thousands of machines in a plant, like you see this machine pyramid that I'm showing you here, there's a lot of different machines. And what we found is, if you've got 3,000 machines in your plant, it's going to take weeks for approval to be able to get, to try a condition monitoring program. It's going to take months to set up the program. What we've seen over the years is, 3 or 4 months later, and you're still setting up the machines, and then upper management comes and asks for what kind of success you've had, and you have to say, well, we're still setting up the machines and we haven't even started collecting data yet, and the program gets canceled. So what we've all learned and best practices shows is the best way to start a program is to start small and grow. And so what I mean by that is, let's start with 10, 15 machines. Let's start with the machines in a small area of the plant. Let's go in and get some quick success. Go ahead and set yourself up for success, not for failure. Let's go and say, hey, I've got these 10 or 15 machines. They're simple machines, they're straightforward machines. I can start monitoring these machines, because you've got to keep a plant up and running. You don't have time to be able to make a condition monitoring program. So the best way to do that is start with a few machines, show some success, get buy-in, prove that the program works, and then grow the program. And we found out that is about the only way to get a program started, is to start small and grow.
Thank you, John. We had another question here. How do you know what frequencies are associated with particular failures? And I think let's see if I can see the rest of this question here. I think someone is asking if there is, if it's a trial and error process, or let me see, or is there some science to it? So speaking to, I guess, the narrowband capabilities of condition monitoring sensors or vibration analysis.
Exactly right. So we kind of introduced this, but yeah, it comes to the same question of there's a lot of things going on in that data way over on the left, and that's why it's almost like getting lost. You can't see the forest through all the trees. If there's just so much stuff going on that you can't see, it's hard to see that. And if we simplify it so that all we get is a number, that makes things a little bit rough too. So that time waveform that I show you in the middle, and I kind of think that's the question that's being asked, is there are discrete patterns. And let me explain that graph in the middle. So if you look at this frequency graph in the middle, what we're plotting here is the frequency from left to right, and we're looking at amplitudes. And each of these vibration peaks, and you can see even in the graph up above in the middle here, you see this very large peak, and that very large peak, for example, with the biggest vibration from a rotating machine is typically from the rotating shaft. So that big peak we see way over in the low frequency, that's quite often the vibration from the turning motor pump shaft. And then these other peaks could be the pump impellers, or they could be other things. And so once we lay out this frequency graph and we identify the speed of the machine, then it makes everything else easy, because that speed of the rotating machine is where we find imbalance. So if you think about it, when you go to balance your tire on your wheel, they do the same thing. They get the wheel turning at a certain speed, and then you'll be able to see that once per revolution thump, and that's the imbalance. And so we know these patterns. Imbalance is going to show up at one times the turning speed of the shaft. Misalignment is going to show up at 2 times turning speed. Looseness is going to show up at multiples of turning speed. So there are 6,000 or 7,000 different vibration rule-based patterns, and of course, I don't want to have to discuss there's the hundreds of patterns, but what we call the big four, because what we find out, keep in mind, I've been analyzing data for over 30 years, and I can count on two hands the number of times I've seen really, strange and rare faults. What we see every day looking at rotating machinery are four faults: imbalance, misalignment, looseness, and bearings. So if we just focus, or if we just take a look at those four faults and learn those four faults, then it's going to make things very easy. So you could just have a vibration expert analyze all this data, but now that we're starting to use it's quick and easy for vibration experts to teach people that don't know vibration to look for those four faults. And also, we can start to use machine learning and artificial intelligence to be able to do some analysis if we're looking for these four faults.
Excellent. I had a comment here from Nigel just saying, I agree 100% on starting small. Asset criticality analysis. It's fun to hear. We had a few questions here. We had one about integrating with eMate, another about seeing if you could get mobile notifications. Is that within scope to talk about here, John?
Sure. Let me jump into that real quick, and I think that I'm trying to think about which one is the best to kind of jump in. Maybe I'll just use this simple one because you're exactly right, or maybe even a better would be, as we look and going from the left and the right, if we get good data, and then we can turn that data into answers. But part of that answer, you know what? I know what slide I need to use, and I jumped into the wrong one. So let me go back and kind of start over again. So we get good high frequency data, and we're able to get the FFT spectrum that we just talked about, and we're starting to see these patterns of imbalance, misalignment, and looseness, and we're starting to get the answers from the data. The next step is we're collecting data with these wireless sensors from many machines in your plant, and instead of with portable data collectors, we're not just collecting data once a quarter or once a month. We're collecting data many times a day. And so if you do the math, you realize that now I've got hundreds of data sets. And even if we've made it easy, like we show here in the middle of the page, who has the time to go look at hundreds of these things every day? We just don't have the time and resources. And so we've got to find a way to quickly go look at data and to be notified when there's a problem. So we need to now have alarms, and we need to have notifications. So the worst thing we can do, and I've seen this happen in a lot of customers over the years, is if all you do is collect vibration data, your vibration sensor can become a data pump. And what I mean by that is it just keeps on pumping out numbers. And pretty soon you just get overwhelmed by all of these numbers. So what we really have to do is, number one, get answers from the data. But number two, we need to get notified when something is wrong. And that's one good thing that computers can do. Vibration experts can analyze the data, but they don't have the time. You can analyze hundreds of set of data every day. There's just no time. That's what computers are really good at. So if we can set up these narrowband alarms so that it will quickly look at it and it will notify us when it sees a high vibration, one of these narrowband alarms. So instead of having to analyze every set of data, we let the software program go in and say, everything looks good, everything looks good. Oops, you've got a peak, you've got a problem, a high vibration, and I think it's in this narrow band that might be misalignment. So we need to have some type of automatic alarm notifications so we know when something, not just high vibration, but a possible fault is starting to occur. Then we're going to use eMate or some other CMMS system to be able to generate a work order. And then that automated work order is going to signal somebody, say, hey, look, we haven't had any alarm notifications for weeks or days, but I'm getting one today, and on compressor one, we're having this high peak, which might be misalignment, and we need you to go take a quick look at it. You go take a quick look at it, and you say, oh, it's there, but it's not bad enough, so let's just close out the work order. So that's exactly what we want to do, is we need notifications to be able to dig through all the data coming in and use our CMMS systems like eMate to be able to automatically generate work order and to make our life a little bit easier.
Excellent. Well, I want to thank all the attendees for all these great questions. We're going to continue going through a few more in the last 15 minutes we have left, and try and get through as many as we can. We've had a couple about, one was about being able to share, having a portal, what you've got on the slide there, the common software portal, to share data with customers and or with others. We can make it more general. And just another question about, which I think ties in, which is how far do you think AI is from being able to diagnose the data as accurately as a human? And so if you could speak to the condition monitoring software element. Also, before you jump in, I just forgot that we were trying to wrap in that mobile question to the last one, and to answer, I don't remember whose question it was, but when you are able to integrate with eMate, eMate does have a mobile app, as do other leading CMMS software. And so you can get work order information, asset information, charge parts, et cetera, work offline on your phone. So that's just to answer that question. But yeah, back to the question at hand, which was about the condition monitoring portal. Can you share your data with, say, a customer or, say, internal sources? And also about AI, and is AI able to diagnose data as accurately as a human?
Yep, those are two great questions. So let's jump into the first one about sharing of data. And that's one of the big things we want to talk about with connected reliability, because in the past, we've had these silos, and everybody knows what I mean by a silo, in that, over here is the data you're getting from your thermography program, and over here is the data you're getting from your vibration program, and here's the data you're getting from this other program. What we need to be able to do is share that information, and that's what's so important about a common software portal, is that we take data from all of these different incoming sensors and tools and different data acquisition places, and we share that on a portal. Now, in the past, what we've done is we've done that over network software programs, but there's a lot of problems with that. One is that every time you write a new software program, then now you've got to generate all the changes out to everybody. So what we found out is that we really need to go to a web-based program, and that's what a lot of people, everybody is going to web-based programs, and I know a lot of people want to have the program, but it's still the customer's data. We're simply putting it on the portal. Why is it important to put it up on a web-based program, on a cloud-based program? And that's so that everybody can access it, because years ago we tried to network software programs, and that becomes an IT nightmare, because what happens is, let's say you've got hundreds of customers spread across different plants across the country, or maybe even different places across the world, and all of them have to have a software license, and all of them have to have access to the network, it becomes a real mess. And what if you want to share that data with your vibration expert or your thermography expert or some other third-party consultant? Well, now you've got to give them a license of the software. But by having these web-based programs, then we as long as they have their sign-in, they have the correct security confidential sign-in, then we can give them access to the data and they can go look at it. And so the data is secure on the web, just like Amazon and all these other web browsers that have these, Microsoft have these very secure web browsers. Well, now we can share that data with everybody in the company that you want to give access to, and third-party consultants and experts and other people. Everybody can have access to the data, but you control who has the access, and you control where the data goes and who gets to use the data. All right. Second question was about AI. The answer to
and that
AI
was specifically on like how far do you think AI is being able to diagnose data? I guess asking about, and I guess we have some things we can talk about in regard to our software, right?
Yep. So the short answer is we've been doing artificial intelligence for years already, okay? We've simply been calling it something else. We've been calling it automated diagnostics. And so basically what automated diagnostics is it's rule-based algorithms. And I told you about the patterns that we talked about. We have 6,000 or 7,000 different rules. We already know what a fault is on rotating machinery. And so we've already built those algorithms, and that's the first step of building an AI. An AI is nothing more than a way of having a computer program be able to go do a lot of the work for us so that we don't have to do a lot of that. And so I would say that we're most of the way already towards AI, and keep in mind also is that where a lot of AI and machine learning is trending simple numbers, what makes it a little more complicated with vibration is that we've got to find a way to screen out the noise and focus on just the faults. We've already been doing that. So I believe that AI is very, very close to becoming a reality because we've already been doing it.
Great. And I wanted to also, I think we got time for maybe a couple more questions. This one, I'm going to try and, again, group a couple questions. You guys have great questions. Thank you, attendees. One was about giving an example of an issue where there's vibration, but it's just not big enough of an issue where a work order would be closed out without action. Wait, let's see. Let me clarify that. Oh yeah, so basically a case where, let's say you get, there's vibration, but the work order is closed out without action. I think kind of relating back to your, example of the, machine is vibrating, but there doesn't seem to be an indication of a fault, nothing narrowband. And then I was hoping maybe you could follow that up with talking about the other scenario of what action should we take when we identify anomalies or trends in the data, and how do we prioritize activities based on this information? So kind of two questions. One about, what's an example of something where we just close out the work order because it's not an issue, and the other's like, what if we do find something? How do we prioritize maintenance activities based on that?
Yeah, those are good questions. So the first one, you're right, because like I said, just because you have a fault, doesn't mean that it's bad enough yet. And so we've read into this quite a bit where, when I was in the Navy working, that often we would see a pattern of a slight bearing wear, and we would send out a report that would say, hey, this particular machine has a slight motor bearing wear. And then the maintenance team would run out and they would overhaul the machine and replace the bearings. And then they would look at the bearings and they'd say, hey, these bearings are fine. And so we would tell them, well, we told you that there was a slight motor bearing wear, but we also, in our recommendation, told you that that just means that you need to keep a close eye on it. So when you think about, again, automated diagnostics or artificial intelligence, or when do I get action on my answers, on my faults, we need to have some steps in that, kind of the way that we've done it in the past is that if you've got a very low vibration that's showing a pattern of a bearing wear, slight would mean no action, where moderate would mean let's keep an eye on it. If we were monitoring this machine monthly, we might want to do it weekly. And then once it gets up to serious, our action might be, let's not act on it now, but let's schedule this for maybe next time there's a shutdown. And then finally, so in other words, what I'm saying is, let's not overreact just because a machine has a fault, but let's look at how that fault has been progressing over time, because like anything else, a fault can go from slight to moderate to serious to extreme over many, many months, and we kind of want to watch how that is progressing. And often what will happen is it could take many, many months as it goes in the lower, but once it gets up to the top. So the short answer is, let's not overreact, and so we would close out a work order if we think we just want to keep an eye on it, and we would only bump up a work order or approve it after we say, yeah, it's bad enough and it's time that we really need to do this. Does that make sense?
Yeah, I think, and then I think we have time for one more. And
what was the second part of that, or do you want to do another one?
Yeah, the second part. The first part was about, I had missed whether you had got both of them in there, but the first part was about when we can close out a work order without even completing it. And then the other part was about how do we prioritize our maintenance activities when we see these anomalies? And I can actually find that question, see if there's any a little more. Yeah. What action should we take when we identify anomalies or trends in the data? And how do we prioritize maintenance activities based on that information?
So I think I've answered part of that in that you would base your repair recommendation based on how bad the fault is and how quickly it's progressing from good to bad. Another thing is another determining factor might be the criticality of a machine, or another might be how important, how long it's going to be until that machine has a repair time. So I think I've kind of answered that a little bit, but just to give a little bit better definition, and the reason we're talking about this is we can make better decisions on when to take a machine down if we've got better information and better trends, and we've been tracking this over time. And so instead of just saying, I'm going to wait until a machine makes a lot of noise, being able to use condition monitoring, we have a much better idea of the condition of the machine, and that way we can make better maintenance decisions on when to take that machine down.
Well, I just wanted to quickly answer one more question that I think I can just answer, which is someone is asking about if Fluke has representatives that help eMate customers analyze their equipment and current structure to provide guidance And yes, there's expert services available for every step in the process, from the tools and the sensors to the condition monitoring to the CMMS. And I think with that, we can wrap everything up right on the dime. So thank you so much, John, for your sharing your insight and expertise. I love going to these myself because I can, you know, I've got to take some notes. So yeah, do you have any comments you'd like to make in closing?
I think in closing, a couple of quick things. Don't fire your third-party consultant, because you need them for the complex machines and complex applications. Find a consultant to guide you past the obstacles on your path to reliability. Look for a solution, not just hardware. Because and one example of that is, think about flip phones years ago. You know, that was a hardware that we all needed, but now we see these smart devices that are connecting us to the internet, to cameras and everything. So it's more than just a phone. It's a solution. It's a communication solution. So those are some of the things that I think we're seeing coming with this Internet of Things and condition monitoring. So I'll leave you with that.
So thank you everyone so much for joining us today. There's going to be a brief survey that will pop up, 6 questions, real quick. If you'd be so kind as to take the time to respond, it does really help us to improve these webinars, and we want to make sure to be giving you the most bang for your buck here. So if you have any additional questions or like to connect directly with the Fluke Reliability team, you can either reach out via the chat, or you can reach out through our website or LinkedIn. We'd love to hear from you. Thank you for your time. Have a wonderful rest of your day. And thank you so much, everyone, for your great questions. Wish we could have had time to answer every last one. So thank you very much, and have a great day.